Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about Thevenin and Norton equivalent circuits. More specifically, we'll be doing these two problems located on the screen here and walking through them. If you want to pause the video and see if you can complete them using these methods, go ahead and then come back to the video and see if you got or received the right answers. So let's go ahead and define the Thevenin and Norton equivalent circuits and why we use them. Specifically, we use them to model circuits as a block with specific inputs and outputs, terminal characteristics, allowing engineers to concern themselves only with the important, only with the input/output of an internal architecture. So if you're given a circuit like this, where let's say that this is your systems engineer and you're trying to create a system, and this is your internal input circuit in blue, but then as a design engineer, let's say I want to attach a buck converter out here. And but then I want to see what my resistance, I want to see what the circuit here in blue, what the output resistance will be, and let's just say RO, and what the voltage will be. Okay, so Thevenin, and then also the current coming in, IO. So I'm curious about all these three parameters, and Thevenin and Norton equivalent circuits essentially allow us to derive our circuit, and imagine this entire thing, into a simple voltage source and a resistor RTH. And then we can always, so there's terminals A and B, where again in this example this would be A and ground would be B, and you can essentially attach your buck converter here. All right. Conversely, you can use source transformation. Again, check out my previous videos to see some examples on source transformation. But you essentially can map this into what we call an R Norton, which is again just R Thevenin, and an I Norton. And you would have again the same thing, terminals A and B, where this is ground, and your buck converter connected to it. So I hope this makes sense of why we do things like Thevenin and Norton equivalents. Essentially, it's to find out of my whole design, which I'm not concerned about, what is my voltage, what is my resistance output, and what is my current output. And these two types of circuits allowed me to find those out. So let's go to the examples, where this is the first example. And in order to find V Thevenin across terminals A and B, what you want to do is you want to open circuit A and B. So I'll get rid of this resistor here. Okay. And you want to basically consider a voltage drop across here, VOC, V open circuit. This is equals to VTH. Now, to find VOC, I'm going to do a nodal analysis across this terminal here. So I'm going to say that this here is a VC. And I'm going to do a nodal analysis. And remember, nodal analysis, you can define your currents. So this is, I said it's I4, this is I3, This is I2 and this is I1. Again, remember, VC is this entire node. So it's the currents being pumped out of that node. And I'm saying that I1 plus I2 plus I3 plus I4 all have to equal to 0. When I do nodal analysis, I1, I start where I1 is starting off at, and then I subtract the voltage source that it's going to, and then divide by the resistance across those two voltage sources. So for example, it would be VC minus 24 over 6 plus, in this situation, this is grounded. So this would be VC minus 0 over 12. Again, these are currents that I'm solving for. So for I3, there's already a current going through it. So I'm just going to add 7 amps. If it was going the opposite direction, if said the 7 amps was going this direction, I would subtract 7 amps. So this is plus 7. And then as you can see for I4, there's a infinite resistance here, right? So no current's going to flow through there. So it's going to be plus 0 is equals to 0. Going ahead and solving for VC, you get VC. You can pull out a 1 over 6 plus 1 over 12. And then this is going to be equals to 24 over 6 minus 7. Doing the algebra on this, you get VC times 1 over 4 is equals to -3. So VC is equals to -12 volts. Again, this is equals to VTH simply because if I consider that my VTH is here and VC is a drop across this resistor and they're both in parallel, voltages in parallel are the same. So this holds true. Okay. Then the next thing I want to do is I want to find my R Thevenin. And in order to find R Thevenin, again, we've done this in previous videos. Please make sure to check those out. What you would do is you would short circuit any voltage source you see and open circuit your current sources. And you'd look in through the output, so plus or minus, this is VORTH. And you would find out that if this is 6, 12, and 2, these two resistors share the same, two nodes, so they're in parallel. So 6 parallel 12 is 6 times 12 divided by 6 plus 12. This will equal 4. And my circuit gets reduced to something like this. 4 and 2. And essentially this is A and B plus minus VO RTH. So then RTH, these only share one node, so they're in series. So RTH is 4 plus 2, which is 6 ohms. So I can then now write out my equivalent circuit and say that my equivalent circuit is a VTH that goes through an RTH. And then we have our terminals A and B. So VTH is equals to well, we would have to switch this minus plus. This would be minus 12 volts and this would be 6 ohms. And we can go ahead and attach our RL. Again, if you wanted to repeat this as a Norton circuit, it would simply be the source transformation. So again, we call this I Norton or I short circuit, and it would be going the other direction because it's going to be negative, and this is going to be equals to, so there's a resistance here, R Norton. There's a mistake there. This would be in parallel. R Norton will be equals to RTH. And we will attach our load resistor here. Again, remember, I Norton is equals to VTH divided by RTH. So this is negative 12 divided by 6, or minus 2. And obviously Rn is equals to 6 ohms. So this would be your Norton equivalent circuit. If you wanted to find your Norton equivalent circuit from the example, let me go ahead and clear this out. So in order to find our I Norton, we can go ahead and attach a short circuit here. So that's why it's called I short circuit. It's also equals to I Norton. And again, let's go ahead and find VC. All right, and find VC again. So VC is the voltage here. So we can define our currents I1, I2, I3, and I4. Remember, this here is 2 ohms. So then VC, I'm just going to go ahead and write the nodal analysis. This will be VC minus 24 over 6, which is equals to I1, plus VC minus 0 over 12, which is equals to I2, plus 7, plus VC over 2, because this now plays a role because I4 is an actual current because it's short-circuited. So this all equals to 0. You would get VC 1 over 6 plus 1 over 12 plus 1 over 2 is equals to 24 over 6 minus 7. This gives us VC times 3 over 4 is equals to minus 3. And if you go ahead and multiply this by 4 over 3, this cancels out, times 4 over 3, you get negative 4. And we can say then that ISC is equals to VC divided by the 2 ohms, which is negative 4 divided by 2, which we get negative 2. And as you see, it's the same thing as we got here, negative 2. So then we can go ahead and write our equivalent circuit as this goes to be in parallel as 6 ohms. This is negative 2. This is A, and this is B, and this is connected to my RL resistance. So I hope this makes sense. All right, let's go ahead and do the second problem. So go ahead and pause the video and try it out. All right, so let's go ahead and find our Thevenin first. And in order to find our Thevenin, what I do is I short circuit the current sources and I open circuit the current sources and I short circuit the voltage sources. And we're looking for RTH at V out. So essentially, imagine this is A and this is B. So I'm going to open circuit my V out and I'm going to look in for RTH. Again, this is 1 ohm. This is 5 ohms. This is 4 ohms. And this is 16 ohms. I'm going to write out RTH in one rotation. I'm going to say 6 plus 16. 4 plus 16 are in series. They're in parallel with the 5 ohm. And that is in series with the 1 ohm. 4 plus 16 is 20. 20 in parallel with 5 is 4. Again, this is just 20 times 5 divided by 20 plus 5, which is 100 over 25. So you get 4 plus 1, you get 5 ohms. So this is equals to RTH. And then the next step is to find VOC. So I'm going to go ahead and redraw the circuit, or I'll copy the circuit. So again, this here is VOC, or again, this is V Thevenin. So I'm going to go ahead and realize that VTH is the same voltage going through here. Let me call this V2. Let me call this V1. And I'm going to go ahead and write two equations for V1 and V2. And when I find V2, that is my VTH. So let's do that. Again, consider the currents are leaving. This is, in this case, I1, I2, and I3. So for node V1, I1 plus I2 plus I3 is equals to 0. This then becomes V1, I1 is just minus 3 plus V1 divided by 16 plus V1 minus V2 over 4 is equals to 0. If I go ahead and multiply this by 16, we get 48 plus V1 plus 4V1 minus 4V2 is equals to 0. So then my first equation will be, this is negative. My first equation will be 5V1 minus 4V2 is equals to 48, equation 1. Okay. For the second equation, let me zoom out here so you can see. In terms of I2, the currents are leaving. So let me consider this I4, I5, and I6. Notice that this is then going to be, so I4 plus I5 plus I6 has to equal to 0. When I write my equations, I4 is V2 minus V1 over 4. I5 is, this is plus V2 minus 12 over 5. And I6 is 0 because, again, this is infinite resistance. So plus 0 is equals to 0. Let's go ahead and simplify this equation. I'll write V1 first. So this is minus V1 over 4. plus V2 1 over 4 plus 1 over 5 is equals to 12 over 5. This becomes minus V1 over 4 plus 9 over 20 V2 is equals to 12 over 5. If I multiply everything here by 20, I would get minus 5 V1 plus 9 V2 is equals to 48. And this is your second equation. You can do some algebra using two equations, two unknowns, but then you get VTH is equals to V2, which is 19.2. So then you can write your Thevenin equivalent as 19.2. RTH is 5, as we got from here. And then plus or minus VO. This was 10 ohms. Again, we wanted to find the voltage Thevenin AB. So this VO is our RL. And this also maps to a Norton equivalent. Again, this is 5 ohms. This is AB, and this is my plus or minus VO 10 ohms, where my this is 3.84, right? My I Norton is 19.2 divided by 5, which is 3.84 amps. If you wanted to find VO now, it's very simple to find that. You can go ahead and do voltage division here and say VO is equals to 10 divided by 10 plus 5 times 19.2, and you get 12.8 volts. So that's your answer. So I hope this makes sense, this concept of Thevenin and Norton equivalence. Very, very important to understand. And it helps a lot when you're dealing with larger circuits. If you haven't done so yet, please comment down below. If you have any questions, like the video, share the video, and subscribe to my channel. Thank you. Have a wonderful day.